So here we're going to take a look at binary phase diagrams. And by binary, we mean that we just have two components, and we're going to describe them as having complete solution, which means that the two components that we're going to describe are going to dissolve into one another with no limits, as we'll see in a moment. So the first example we're going to take will involve H2O. And let's say we have a temperature axis, this vertical axis here, where we imagine increasing the temperature of water until it boils. That would happen at 100 degrees centigrade. Any temperature below this, then the system would be entirely liquid. Any temperature above that, and we would have vapor. So water, pure water, is a very sharp melting point of 100 degrees centigrade. This sharp melting point is characteristic of pure substances, whether it's pure elements like oxygen or nitrogen or iron or gold. Any kind of pure element or pure compound like H2O is going to have very sharp melting points and very sharp boiling points. Let's take another example. Let's say instead of water, we'll draw another vertical axis. We'll just put it over here. So again, this is temperature increasing upwards. Let's say our other substance of interest is a type of alcohol, ethanol. This is C2H6O, or we can write it as C2H5OH. This second formula is better, probably because the carbon atoms are attached not just to hydrogen atoms, but also to a hydroxyl ion. Anyway, we don't really care about that. Let's just assume that for our purposes that we just have this pure stuff, and it doesn't really matter how we write it. Well, pure C2H6O is going to have a boiling point that's a lot less than water. Instead of 100 degrees, it'll be about 76 degrees centigrade. Not exactly that, but close enough for our purposes. So anything below 76 and ethanol will be pure liquid. Anything above 76 and it'll be pure vapor. It doesn't matter how far above or below we are compared to these reference temperatures. So for example, something at 99.9 degrees centigrade, just a tenth of a degree below this, that system, if it's fully equilibrated, should be entirely liquid with no vapor bubbles at all. There might be a couple of vapor bubbles, but left at that temperature for a long enough period of time, they should disappear. On the other hand, if we have something that is at 100.1 degrees centigrade, just a shade above the boiling temperature, there should be no liquid at all, and the entire system should be vapor. But what if we have a mixture? So let's draw a horizontal axis that connects these two. So let's say we have some mixture of ethanol and water that are dissolved together in one another. And H2O and ethanol are a complete solution. We can mix them in any combination we like. They are not immiscible liquids like, let's say, water and oil or vinegar and oil. So we can write the composition a couple of different ways. We'll write it as X sub E, where this is the amount of ethanol, and that would be 0 for the case of pure water, and 1 for the case of pure ethanol, which would be the same as 100% ethanol. We could also write it as a fraction of H2O, where we would have 0 over here, and it would increase to 1, or a percentage of 100% for the case of pure water, but it's a little bit easier to read left to right, or at least our habit to do so, so we'll use this case here. So let's say that X sub E equals 0.5, so we have something that is half water, half ethanol, 50% of each. Well, if we take that mixture and start heating it up, it will begin to boil at a temperature that's lower than 100 degrees, but higher than 76. We'll just put it here. The precise value doesn't matter for our purposes. But it's not going to be a sharp boiling point. We're going to have a boiling interval. So we'll have liquid down here, but there will be an interval over which, while we heat it up, liquid plus vapor will coexist until we finally reach a final boiling temperature above which we'll have only vapor. So here, this temperature interval, we can draw some horizontal lines, or as horizontal as I can draw them. This will represent a boiling interval. So that is the temperature increase that we need to have to get from the liquid to the vapor state. Notice there's no such interval here. This interval collapsed to 0 for the pure substances. And if we pick something that is, let's say, very rich in ethanol, let's say X sub E equals 0.85, we would have a much narrower boiling interval. instead of the wider interval, then we'd get it, let's say, 50%. And so we might go from liquid to vapor with a much smaller temperature increase. And by the same token, if we go closer to the water apex, we would also have a smaller temperature interval. And we can connect all these to create a curve. And it's probably going to be easier to simply erase the chalkboard and redraw this whole thing so we can show those curves. So we'll have pure H2O over here, and we'll have pure ethanol over here, and we'll have this vertical axis that represents these mixtures, and then we'll have a curve. This is not meant to be a straight line. We'll try to make it curve a little bit more, and then another curve down here, and this temperature is 76 degrees centigrade, and this temperature is 100 degrees centigrade. So we have a broad boiling interval over here, a smaller boiling interval over here as we get close to the water end of this binary diagram, and then also a smaller interval here. And these boiling intervals disappear when we finally reach the pure substances, and they boil at a very sharp boiling point. So the key thing here is that mixtures, things that are mixtures of two or more things, are going to have a boiling, or as we'll see later, also a melting interval, while pure substances are going to have a boiling point, a very sharp boiling point. So water, a boiling point, ethanol, a boiling point, but a mixture of, let's say, let's say something that is here. Where would that be? This is at about x sub e equals, 0.25 more or less. No, it doesn't matter for our purposes. If we have this composition and this temperature here, we would have a mixture of liquid plus vapor. The system will begin boiling here. That's the beginning of the boiling interval. It would end boiling here. So that's the boiling temperature interval shown here. If we pick an arbitrary temperature in between, we would have a mixture of liquid plus vapor. Anything that falls within this envelope here is going to be a mixture of liquid plus vapor. Anything that's below this curve here will be liquid. So everything down here will be in the liquid state. Everything up here will be in the vapor state. Everything above this curve here will all be vapor. Anything in between is going to be a mix. Let's draw one last diagram. So we have H2O over here and ethanol on this side. And again, we've got this horizontal axis that represents a change in composition. And we have a curve, sloppily drawn, maybe a little bit better drawn down here. Liquid here, vapor here, and the mixture of liquid plus vapor here. So if we take any arbitrary composition, let's say this one here, at this temperature it will be completely vapor. The intersection puts us in this vapor field. If we have a lower temperature here and the intersection is in this envelope here, then we would have a mixture of liquid plus vapor. So this is going to be entirely vapor, whereas anything below that point will be in the liquid state. So down here, anything at any temperature, let's say down here, we would have liquid and liquid only. Take another composition over here. At this temperature, it's going to be a mixture of liquid plus vapor. Heat it up, up here, it'll be entirely vapor, and down here it'll be liquid. So we'll look at how this relates to the compositions that are created in our next video. But the key point behind our video here is that we just want to illustrate that there are sharp boiling and melting points for pure substances, but melting intervals and boiling intervals for mixtures, for things that are in